Hey guys, what's going on? Mr. McBain here again. We're now going to look at applications of linear modelling. Pardon me. And in other words, solving problems using linear equations. Now, one of the key things that's going to help you is the idea of rates and gradients. Now, often in a linear modelling question, there might be some information about a speed. Something might be travelling at a certain speed, or someone might be charging so much money per hour of work. Each of these is called a rate. So, for example, speed, if we think about speed for a second, speed is measured in kilometres per hour. That would be one way of measuring speed. You could also measure speed in metres per second if you wanted. We can measure a pay rate in terms of dollars per hour, or you can be confronted with a problem where they charge so much money per item. For example, I've noticed that there is a problem involving a company that cleans bedrooms, and they charge so much money per bedroom, so dollars per bedroom. A production line might be able to manufacture so many cars per hour, or so many items per hour. I was right, items per hour. So that's like a production line. Now all of these are examples of rates. So when you see any sort of information in a problem where it's so many items or so many things per something else, that's called a rate. So if you can write the information in terms of something per something, we call that a rate. And what's really critical for your understanding of linear equations is to recognize that the rate is always the gradient in a linear equation. So what I mean by that is if you were doing a job, for example, and you were earning $28 per hour, $28 per hour, that is a rate. And so you could write that as a linear equation. How much you earn, your earnings, will equal 28 X, where X is the number of hours you've worked, and that's the number in front of the X, that's your gradient, and in this case it's the rate, it's your pay rate. So if I want to be even more streamlined about it, I could call my earnings Y, so you could write that finally as a linear equation, Y equals 28X, and you could sketch that on a little graph, Y versus X. Y is your earnings, X is your number of hours worked. This is just a quick sketch, and the gradient of that graph would be 28, because that's your pay rate. Okay, so that's really important. So going back to the main part of our lesson then, we're talking about linear modelling. Remember, a rate is the same as the gradient. Okay, so let's put this to use. Let's say that there is a sample problem. I'll do one out of the textbook so that you can cross-reference it. And the one I'll pick is on page 127 of your textbook. So we've got Optus, our telephone company, offering two packages for their customers. So here's it's a comparison of two different telephone contracts. Contract 1 or package 1 tells us that you pay $21 a monthly service fee, so it's $21 each month, and you pay 14 cents per call. The second package, package number 2, you're charged a smaller monthly fee of only $7, so $7 each month. But I imagine, I haven't even looked at the problem yet, but I imagine the call rate will be higher. And yes, it is. It's 28 cents per call. So under the question, it's got a whole lot of after the original statement, it's got a whole range of questions for you to answer. We have to find the equation to represent each of these packages. We need to graph the equations, and we need to find under what circumstances package 1 would be cheaper, under what circumstances would package 2 be cheaper. So let's now convert these. The first step is to convert both these packages into a linear equation. So let's have a look at our information. Let's look at package 1 first. Here, let's find the rate. Here's the rate here. 14 cents a call. So our rate, we're being charged 14 cents per call. So that's our rate. I'll write that down over here. And by the way, I'm not going to write 14 cents. We're going to work in dollars, so it's going to be 0.14. So $0.14 per call. That's our rate in this case. In the second package, it would be $0.28 per call. And these values over here, this is how much you just have to pay regardless of how many calls you make. You've got to pay at the beginning of the month, you've got to pay $21 on this plan, and you've got to pay $7 on this plan, no matter what else you do. So if we now sketch, if we now let C equal how much is going to cost us per month. So let's define our variable. C is the cost, total cost per month. And we will let N, I think that's the variable they've chosen, N equal the number of calls. Or C, we could just write C as cost if we like, make things a little bit simpler. But we're dealing over 1 month. So C is cost, how much we pay, and N is the number of calls that we make. So in terms of linear equations, this is going to be similar to our y-axis, and this is going to be similar to our x-axis. Okay. So if I now write the equation, let's look at the first one, the first package, package 1. C, the cost, is going to equal, well, remember, the rate is the gradient. Now, the rate is 0.14, so it's going to be 0.14. Now, it's not x, it's n. So, 0.14 n, there's our call, there's the rate associated with how much we're charged per call, and plus on the end is how much we get charged regardless. So, this is like a fixed constant. We have to pay $21 per month, no matter what else. In package 2, the cost we pay each month will be the rate. Now the rate in this case is higher, it's 0.28 times the number of calls, but the monthly fee is less, so plus 7. So there's our two equations. And this actually looks very similar to simultaneous equations, where we've got two different lines or two different linear equations and we should compare them. So we could do that, in fact. So I'll draw a set of axes over here. Now, this is just a sketch. Of course, you can use your calculators here to help you. But if I now look at package 1, my intercept, the number on the end, will be 21. So I'll mark that up about there, 21. And the gradient's quite small, 0.14. Now I'm not going to actually measure it out, but it's going to be quite a low gradient, so it's going to be quite a shallow line. So something like that. And I'm going to just connect those lines with a little ruler here. But remember, if you're doing this on your calculator, you'll get much more accurate graphs. The second equation, so that's package 1. Oops, that's package 1. Always label your graphs. Package 2 has a lower intercept, so it's starting at a lower point, about 7, but it's got a higher gradient, so it'll go up steeper. So it'd be something more like maybe something like that. Okay. And that's package 2. Now, we can see there's a point here where the two graphs cross, and we know all about that because we've studied that in the past. If we want to find that point, we would solve these two using simultaneous equations. But let's have a look at what happens either side of it. If we stay to the left of this line, you can see that package 1, sorry, this is package 2 here. Package 2 along here, for a given number of phone calls, there's our number of phone calls along there, this is N and this is C. If I made that many phone calls, then that's how much I would pay if I was in package 2. That'd be the amount I pay. If I was in package 1, that's how much I'd pay there. I pay more. So you can see, hopefully, that if I keep my number of calls below this critical value here where the two graphs cross, in there, then package 2 is going to be cheaper. But if I make more calls than this value, if I start making calls at this number, say this many calls up here, then you can see now package 2 becomes more expensive. And so that's why this is a really practical example of you being able to use linear equations, because if you're comparing rate phone plans, if you can work out or estimate how many calls you make a month, you can decide which is the cheaper plan for you. And so it all depends on your ability to calculate that point. And so in order to do that, you would solve these equations. Now, I'm not going to go over that with you now because that's something that you've done in the past. I think you know how to actually solve these equations. You can go through the working in the book as well. But when you solve this equation, you end up with an xy value that represents that point, and that will be the coordinates of that point. So that's an example of how we can use modelling to solve problems. Now just remember, the key point I want you to remember out of all of this is that the gradient is the rate. Okay, so work out what's the important rate in the problem, that becomes your gradient. Make sure you define your two variables. Now it won't always be x and y as we've just seen. In this case it's c and n. You need to decide what your variables are and define your variables, work out what the gradient is, determine the equation of each of your different comparisons, and then sketch the graphs. So that's basically the logic you use in every one of these problems. And so all those problems in chapter 3F, applications of linear modelling, use a similar approach. Look for the rate, define your variables, write down the equations and sketch them, and often, if it's a comparison, you will need to find the simultaneous solution, in other words, the point where the two linear equations cross. Okay, well I hope that's helped you. So these two videos hopefully have given you the information you need to complete 3E and 3F. Okay, thank you very much. Bye.